Okay, there you are.
Can everyone see my screen?
Yeah, perfect.
Okay. Let me. Okay. All right. So for this seminar, I'm going to kind of change gears a little bit and going to go over two examples using BERT. And then both of these, kind of just a note, are using TensorFlow implementations of BERT. So kind of starting out, one of them is going to be a movie review sentiment classification. So basically kind of analyzing the content of a movie review and then classifying if it's positive or negative. So, you know, what the polarity of that review is based on kind of the content. And then the second one we're going to look at is a classification problem using the 20 News Group data set. And that's going to be kind of given the content of these news articles, can we classify them into different groups in different classes based on that? So I'm going to start with the movie review sentiment example and just kind of step through the code. Once I finish the first one, then we can kind of talk about it a little bit. If you have any questions anytime, you can jump in, and then, you know, I'll move on to the next one. Okay, so again, I'm using TensorFlow. Both of these are going to be using TensorFlow implementations. Okay, so start with kind of loading the data. So again, this is using the IMDb movie reviews. It's a public data set. You know, here they have kind of it hosted in a few different places. Here I'm importing it from Stanford's kind of AI, you know, place. So yeah, this data is, you know, it's public. And they have both, you know, labeled training set as well as a testing set that, you know, also has labels so that we can verify our modeling. So we're going to create a class here, and we're going to be kind of tokenizing these based on sentences. And the labels, again, are going to be the polarity of the actual review. So kind of a few things to note. The way we're setting this up, the max sequence length that it's going to allow for this movie review data class for the tokenizer is going to be 256. But I believe I'm going to be using a much smaller sequence length, about 32, as we go on. So here we're setting up the tokenizer. You know, we're passing a sample size and max sequence length, and then we're loading the data sets from that URL showed you before.
Now, I may be asking a stupid question, but I don't know enough Python. No. Why do we need to use this self dot something?
So this is a class. So it's setting it up to, and when you define a kind of the initializing function of a class, you have to use these kind of self dot function calls.
Mark, I can probably explain that.
Yeah, tell me.
If you I know you're more of a Java guy, Mark, so I can explain
Yes,
Java.
and so that would be this in Java and why?
In Python, unlike Java, if you're going to refer to a variable that's part of the object, you have to refer to it with self. And in fact, a class method always has to pass a reference to self with the it'll be implicitly passed to the method call. So it says self here, although you wouldn't explicitly put self when you make the invocation, but that's how you're able to refer to members of the class, is via the self. Unlike in Java, you can't just say tokenizer. You have to say self.tokenizer.
Oh, so I always have to do it, right? Is it being created at this time, or is it declared somewhere else?
Oh, Mark, I might be, if I could jump in just because the problem with Python in terms of object-oriented, Mark, is that objects are not a fundamental construct in the language. So we kind of add them onto the language. So we got to put the glue to kind of put all the stuff together in a class. Mm-hmm. So self just means that this is an instance variable or an instance method.
For that
in Java, that's behind the scenes because of the language. So you don't actually see it, but you do see it when you have to use the this operator. Mm-hmm. This is equivalent in Java to self in Python, but we're just having to do with the fact here that the classes are not a fundamental construct in Python.
Okay,
so we're just grouping stuff together.
That's I get it. Is it being created? That's the declaration of that at this time?
Yeah. Okay. So when the class is an object is originally instantiated, the init method is run as a constructor.
Mm-hmm. Okay. Thank you.
Okay. Glad to help. Thank you very much.
Okay, Matthew, thank you.
All right, so so we're setting up a few different things in here. Setting up, the training and testing sets. So again, both the X in this case is going to be those tokenized sentences, and the Y is going to be our polarity labels.
Okay, Matthew, that code must have come from somewhere, because somebody needs to know the internal format of movie review data set. Is that true?
Yes, I believe Tim. I don't know if Tim made this, but he provided this to me, and then I had to kind of change it up to fit with TensorFlow 2.
I think I hacked this up from a TensorFlow 1 example that I had originally gotten from Google. So yeah, but I made a number of changes to it. So yeah, I think that's kind of the story of that. Yeah, but yeah, one of the things I asked Matt to do is to upgrade it to TensorFlow 2. Mm-hmm. So
makes sense.
But yeah, you really do have to, a lot of this is with kind of the implicit understanding that you have of this movie review data set. But yeah, so then for the tokenizing step, for kind of the reiterate what we've been talking about with BERT. So we're tokenizing just like with pretty much every other NLP process, except we have to add in a special type of tokens. These CLS separators, which kind of are at the beginning of each of our sequences, and then the separation, the sep, which is at the end, will kind of separate each sentence in our sequence. And then, finally, we have to do some padding to make all of our sequences, the same length. So in this step, I'm just downloading or copying the BERT weights locally. So that's all this is, and particularly I'm using the uncased, I believe it's the medium size BERT. Okay. So now So kind of the first step, tokenizing. So we're using BERT's full tokenizer as implemented in TensorFlow. Again, using the copied, vocab and pre-trained BERT weights. And then kind of using this tokenizer, setting this sample size and a max sequence length, in this case of 32. Kind of played with a few other sequence lengths, but that in BERT, it seems like, I guess with a lot of NLP, I mean, someone else might be able to jump in on that, but with BERT, it seems like kind of a smaller medium sequence length typically works better, but there's kind of different things to play around with.
I think that's an important place, right? I believe that is how much text is being analyzed at one time. So if your entry is longer than this in words, I believe, then it just wouldn't work, correct? And so I believe that the model does either 128 or something else.
Yes.
And that's a limitation. I understand why smaller sequences would work better, just because they're smaller, easily to target, and especially for movie reviews, which are very short. So we probably don't consider anything that's longer than 32 words. But in practical life, that's a limitation. Tim, what do you think? Tim thinks nothing. So we will be back to that. And since I'm talking anyway, I'll warn everybody when the meeting suddenly ends. When it suddenly ends, which is in 8 minutes from now, you'll just join it again. I'm sorry for that interruption.
Okay, sounds good. Okay, so let's kind of take a quick look at what our training data looks like. So again, these are kind of movie reviews, and they're split into individual sentences. And so the original data set actually has a kind of traditional 1 to 10 movie rating. But for this purpose, I've kind of changed it to a 0 or 1 polarity. So 0 being negative, anything below 5, and then a 1 for anything above 5. So 6 to 10. So based on the kind of tokenization step, and we've created these arrays for the different for our training data and our testing data. And that 32, again, that's our max sequence length, so that's going to be the size of those arrays. So after encoding, this is what these arrays look like. Again, you can kind of see with the padding to make sure everything's uniform. And
how does the padding work? I think it tells me we're adding empty tokens in front. Is that true?
I believe it's at the end.
At the end?
Yes. Typically, I think padding's, you're usually adding empty tokens at the end of the sequence.
Okay, fine.
Yeah, so this 0 token ID multiplied by the max sequence length. So I guess you're adding these 0 tokens at the end of the sequence until it reaches that max length. But if that's wrong, someone else can kind of correct me on that. Okay. So we also have, I don't use it in either of these examples, but this was kind of set up as well. in case I don't want to dive too much into, adapter BERT and its use, because that's kind of like a different rabbit hole. But that's an option as well, which is essentially just kind of freezing some of the BERT layers so that you have kind of less trainable parameters is what, kind of what I
So which I always understood you freeze the previous layers, those that come from the pre-trained model.
Okay.
The only layer that you keep up for optimization, that was the one that you added with the movie reviews.
Got it. Okay.
I think that's it.
So you're not doing any fine tuning of the BERT layers at all.
No, but I think that is a possibility. It's not that it is always have to be this way. No, you can go more complicated than what we're doing here.
Right.
Hi, this is Paul.
Yes, Paul, tell us.
Hi, yeah, actually, I want to make a comment about that. I noticed that people are often unfreezing all layers in BERT to do fine tuning. Actually, I see that, and I'm doing that in my recent project. In contrast to the more commonly known case of just doing the final layers.
And I think that's how it is in the paper. But you're saying that you start from the given values, and then maybe you will be fine-tuning a little bit of all of the layers, right?
Yeah, it's actually a surprise to me, but this is what they do in the research code for BERT.
Wouldn't it require a lot of computing capacity?
Absolutely. The fine-tuning is extremely slow.
And you mean when it is frozen, still slow? Because the lab runs in about maybe an hour, but it does finish.
Yeah, that's right. You do have to compute all layers anyway. So maybe it wouldn't matter how long it, whether were fine-tuning or not. But yeah, I had like, 20,000 examples on a CPU, only 36 hours for fine-tuning.
Okay.
15 minutes on a TPU.
Okay. So the advantage is that you still start with much closer values, right?
Oh, you still do. Exactly. Yeah. It's like one of those, you got lucky in the network. You picked the right initialing starter conditions kind of thing. Yeah.
Very lucky. Somebody gave you that luck. Okay.
Yes. Pretty extreme luck. Yeah. Uh-huh.
Right.
Yeah. But I often wondered what would it be like to only do a final layer in BERT. And sorry, late to the meeting. My machine had some issues and had to restart a couple of times.
And it will restart in a couple of minutes, so we'll rejoin. I need to mention, since that we're all recording, that I really wonder how that would look in Hugging Face, because I think Hugging Face will give us code that will be like 5 to 10 times shorter. It will be a very interesting comparison.
Oh, for sure.
I've been working on experimenting with Hugging Face now.
Okay.
So but I don't really have any information on the timing of that. But that would be interesting to see. So I'm a little bit surprised as well about unfreezing all of the layers, just because our experience with transfer learning in other areas, the conventional wisdom is that the first few layers is relatively pointless to unfreeze, because of the idea that those are kind of it's more generic, and it's the later layers that are the ones that that fine tuning is more effective. But it's interesting that wasn't the case when you experimented with that. So